Continuing our study of enumerative combinatorics, we're going to be learning about something called binomial coefficients. So let n and k be two natural numbers. Then the number of ways to select k objects out of n labeled objects. So n represents the total number of objects you have, and they're all distinct. They can all be labeled. And we want to select k of them, is given by the following formula. N factorial divided by k factorial times n minus k factorial, provided n is at least as large as k. But if k is actually larger, then the result is 0. Well, if k is larger than n, k, remember, is how many objects we want to pick, and n is how many objects we have. If your goal is to select more objects than you have, you can't do it. So there are 0 possible ways to complete this task. So from now on, let's go ahead and assume that n and k are chosen so that k is less than or equal to n, but they're both bigger than or equal to 0 because they are natural numbers. We're going to be considering selecting our objects with order. In other words, I'm actually going to keep track of which one I chose first versus which one I chose second, and so forth. Since we have n objects, there are n ways to choose the first object. Since I've already selected a single object, there are only n minus 1 ways to pick the second. Okay, observe that the first object has n minus 0 choices. The second object has n minus 1. The third object would be n minus 2, different ways of choosing. The kth object is n minus k minus 1. So that would be the number of ways to choose objects with order. But we don't really care what order we pick them in. If I pick the letter A followed by the letter B, and then I pick the letter B followed by the letter A, at the end of the day, I've chosen the same two letters. Those are not two distinct choices. So we've actually overcounted. Okay? If all I do is keep track of how to choose objects with order, I've overcounted based on how many ways I can order objects. And since we chose k different objects, there are k factorial ways of ordering them. So the total number of ways we can complete this task, well, our numerator is given by this product, n number of ways to choose the first object, n minus 1 to choose the second, all the way until n minus k minus 1 to choose the kth. We multiply these all together because there are k different tasks to accomplish, but we have overcounted by a factor of how many ways to order the k objects we've chosen, which is k factorial. Now observe, this numerator counts down from n minus 1, all the way down to n minus k minus 1. What if I kept counting n minus k plus 1, all the way until I count down to 1? Well, I'd have to introduce those terms into the denominator. So in this term, I could cancel this with this all the way down to canceling 2 with 1 and be left with what's right here. The reason that we've gone through the trouble of introducing all these extra terms in both the numerator and denominator is because now the numerator is a product that counts down from n to 1. That's n factorial. We already had k factorial here, and this is now a product of n minus k all the way down to 1. In other words, n minus k factorial. So this quantity, the number of ways to choose k objects out of a collection of n, is called a binomial coefficient, and we also say it as n choose k. The notation is here. N choose k, you put these big parentheses around, and n on top, k on bottom. It is not a fraction. Do not draw a fraction line between them, because then you would just have the fraction n over k. But if you simply draw big parentheses, and the big parentheses are important, n on top, k on bottom, it's the binomial coefficient n choose k, and it's computed as n factorial over k factorial times n minus k factorial, unless k is larger than n, in which case the result is 0. Observe if k is larger than n, down here you'd have a negative number, and negative numbers do not have factorials, so that would be your big clue. If k is larger than n and you attempt to use this formula, you'll have a negative number factorial which doesn't exist, and that would remind you, oh, if k is larger than n, the binomial coefficient actually computes to 0. In the study of binomial coefficients, a very handy thing to have at our disposal is something called Pascal's identity. For any two natural numbers n and k, n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. This will always hold. Well, we're going to prove it in a few distinct steps. First, what if k is bigger than n? Well, if k is bigger than n, k plus 1 is even bigger, so it's definitely bigger than n. But also by adding 1 to both sides here, k plus 1 is larger than n plus 1. Term by term, k is bigger than n, k plus 1 is bigger than n, and k plus 1 is bigger than n plus 1. You cannot choose more objects than you have, so all three of these would evaluate to 0. So in the specific assumption that k is larger than n, all we have to check is 0 plus 0 equal to 0? Spoiler alert, yes. Well, what if k isn't bigger than n? Then maybe k is equal to n. Well, if k is equal to n, then k plus 1 is definitely bigger. So if k plus 1 is bigger than n, this middle term here is still definitely 0. However, if k is equal to n, then k plus 1 is equal to n plus 1, so both of these terms do exist. So let's work from the left. N choose k can be computed as follows, but n is supposed to be equal to k, so I'm going to replace all of my k's with n's. N minus n is definitely 0. 0 factorial is 1, it is not 0. So n factorial over n factorial times 1 is just n factorial over n factorial. That's just going to reduce down to 1. But very similarly, n plus 1 choose k plus 1. Remember, n is equal to k. So this k can be replaced with n. That's going to reduce down to this, and here I get n plus 1 factorial over n plus 1 factorial times 1. Remember, 0 factorial is 1, which is also going to simplify down to 1. So in the specific assumption of k equals n, 1 plus 0 equals 1, which is also true. So the only thing we have to check is what if k is smaller? If k is larger than n, everything was fine. If k equals n, everything was fine. So what if k is smaller than n? And observe, both have to be bigger than or equal to 0 because they are both natural numbers. Well, if k is less than n, then k plus 1 is less than n plus 1. But also, since they're natural numbers, if k is less than n, I can add 1 to k and definitely not be bigger than n. I might be equal to it. For example, 9 is less than 10, but when I add 1 to 9, I am now equal. But k plus 1 will definitely be less than or equal to n. In other words, k is less than n, k plus 1 is less than or equal to n, and k plus 1 is less than n plus 1. So all three of these terms can be computed using that formula involving various factorials. Then let's take a look at the left-hand side here. N choose k plus n choose k plus 1. N choose k is computed as n factorial divided by k factorial times n minus k factorial. And n choose k plus 1 is computed as n factorial divided by k plus 1 factorial times n minus parentheses k plus 1 factorial. And if you distribute that minus out, you get this right here. All right, this is a complicated line, but let's look term by term what we're doing. First term, n factorial over k factorial times n minus k factorial. Multiply the numerator by k plus 1, but also multiply the denominator by k plus 1. This is legitimate because these could be canceled out to not really change anything. So this k plus 1 cancels out this one, so that's fine. N minus k factorial. Remember the recursive relationship for factorials. A factorial number is equal to the previous factorial times the last number that you would multiply. For example, 8 factorial is 7 factorial times 8. N minus k factorial is n minus k minus 1 factorial times n minus k. This factorial is the previous factorial times the last number. And then in the other term, we do something very similar. The numerator we multiply by n minus k, but we also multiply the denominator by n minus k. So these would cancel out, and that's okay. K plus 1 factorial can be replaced with the previous factorial, k factorial, and the last number, k plus 1. So k plus 1 factorial is equal to k factorial times k plus 1. Now, why would we go through all the work? This term is equal to that, and this term is equal to that. But now observe that their denominators are identical. We've given them a common denominator, so we can add them. The two numerators both have a term of n factorial. So I have this common denominator, and the numerator is n factorial times k plus 1 plus n factorial times n minus k. And I can factor that n factorial out. N factorial times n minus k plus k plus 1. So now we're still looking at the left-hand side here, and we're going to hope to make it equal to the right one. So let's continue working with where we were. We have already established that n choose k plus n choose k plus 1, under the assumption that k was strictly less than n, could be represented as such, Now that they had a common denominator, we can write it like this. Here's the last line on the previous slide. Now in this parenthetical term, of course, notice we have a minus k plus k. Those cancel out, giving me just n plus 1. However, down here, we have n minus k minus 1 factorial times n minus k. A previous factorial times the next number, that can be replaced with the next factorial. And k factorial times k plus 1 can be replaced with k plus 1 factorial. A previous factorial times the next number is the next factorial. Now in this term right here, we have n minus k factorial. This happens to be equal to n plus 1 minus the quantity k plus 1. If you distribute this out, you'll get an n minus k, and the ones would cancel. So yes, this is equal to that. But that's exactly n plus 1 choose k plus 1. Top number factorial, bottom number factorial, difference factorial. So overall, n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. On the previous slide, we manually took care of what if k is larger than n. We got 0 plus 0 equals 0. What if k equals n? We got 1 plus 0 equals 1. And now here, at long last, if k is actually smaller, it does work out. Pascal's identity is always true for any natural numbers n and k. There's another version of Pascal's identity that's worth taking a look at. For any n and k, here we have it, n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. We've already established this. But we're going to do this using a counting argument rather than that purely algebraic one. Suppose you have n plus 1 elements. Okay, so out of n plus 1 elements, we're going to eventually choose k plus 1. One of them we're going to designate as special. If I'm supposed to choose k plus 1 elements out of n plus 1, there are two distinct possibilities. Maybe I picked the special element, and maybe I didn't. So let's suppose we have one special element and n normal elements. That gives me my n plus 1 special element, total elements. Either I can pick a total of k plus 1 normal elements, totally ignoring the special one, or I can pick the single special element, which remains k, total things to choose from the normal ones. So there are two distinct possibilities. Out of n plus 1 elements, if I'm choosing k plus 1, perhaps all of them were not the special element, or maybe I did pick the special element and then I had k normal ones to pick. So we're going to choose the number of ways to do this. We are choosing k plus 1 elements out of n plus 1. Suppose that one of these elements is special. Either we choose the special one or we don't. Suppose we do choose the special one. Then I have k more elements to pick out of n non-special elements. So there are n choose k ways to do that. That was choosing k plus 1 elements out of n plus 1, assuming we did pick the special one. If you're choosing k plus 1 elements, split it into two tasks. Pick the special one, there's one way to do that. Then, from the remaining n elements, pick the remaining k that you need to choose, and there's n choose k ways to do that. That takes care of how you can go about things successfully picking the special element. But what if you don't pick the special element? Then you have to pick k plus 1 elements all from the unspecial elements, and there were n of those. So you're trying to choose k plus 1 elements out of n because you are specifically not picking the special one. So there's this many ways to choose the special object and this many ways to not choose the special object. Altogether, the number of ways to choose k plus 1 out of n plus 1, pick one of them to be special. Maybe you do choose it, in which case there's k ways to choose out of the remaining n. Or maybe you don't choose it, in which case you have to choose all k plus 1 objects out of the n unspecial objects. So by counting our elements cleverly, we were able to establish Pascal's identity in a different way. Well, let's take a look at another bin sorting problem. Suppose we have n unlabeled balls and k labeled bins. Also, we do require ourselves to at least have one of each. The balls do not have labels, but the bins do. What we're doing is we're going to count how many ways to distribute balls into bins. The answer is going to be n plus k minus 1 choose n if there's absolutely no restriction. Any balls can go into any bins. K choose n, however, if each bin can have at most one ball, and n minus 1 choose n minus k if each bin can have at least one ball. So in the first version, there's no restrictions at all. Okay, balls go into bins and it's a free-for-all. In the second, however, we are not allowed to have a bin with 2 or more balls. Every bin can have at most 1. And in the third version of this problem, you're not allowed to have empty bins. Each bin must have at least 1 ball. Recall that the bins have labels, but the balls don't. Okay, so it doesn't actually matter which balls go into which bin. We're only keeping track of the total number of balls into each bin. So each bin number can be considered to be attached to how many balls it ends up with. Okay, if bin 1 has 3 balls in it, I don't really care which balls they were, just that there were 3 of them. For the second problem, okay, put aside the first one, we're doing the restriction now that each bin can have at most 1 ball. So there are k different bins, and we simply choose which of them get a ball compared to which don't. I'm not allowed to put 2 balls into a bin, so the only choices are either a bin gets 0 balls or it gets 1. Well, I had a total of n balls to distribute, so out of the k total bins, choose which n of them get a ball. K choose n. Now observe, of course, if n is larger than k, if I have more balls than bins, this binomial coefficient spits out a 0, which makes sense. If I have more balls than I have bins, by the pigeonhole principle, there's no way to distribute them without getting a single bin having at least 2 balls in it. So for this third variation on the problem, we have n unlabeled balls, we have k labeled bins, we want to distribute them, and we're not allowed to leave any bin empty. The claim is that the number of ways to do this is n minus 1, choose n minus k. The proof is going to be based on a technique called double induction. You see, we have 2 different variables, n and k, that are both allowed to be any natural number, so we're going to need to do a proof by induction that accounts for 2 different variables. Here is a formal statement of the claim we've made. For any k bigger than or equal to 1, and for any n bigger than or equal to 1, the solution to the problem is given by n minus 1, choose n minus k. As a base case, let one of the variables be its base value, which in this case is 1. Then formally the claim becomes, specifically for k equals 1, for any n, the solution to our problems is n minus 1, choose n minus k. Now you can proceed by inducting on n, because in this particular statement, k is fixed at 1, and now n is anything bigger than or equal to 1. And you can say, as a base case, let n equal 1, and then do an inductive proof based on the variable n, while k equals 1 is fixed. It's actually not necessary to do that in this problem, however. It doesn't really matter what n is. If k equals 1, we only have a single bin. So how many ways can I distribute balls into a single bin? There's one way to do that, put all the balls into that bin. And observe, if k equals 1, you get n minus 1 over n minus k, n minus 1 choose n minus k, is n minus 1 choose n minus 1, and that's going to reduce down to 1. You compute this through its factorial formula, and indeed, how many ways can I choose n minus 1 objects out of n minus 1 objects is 1. So if k equals 1, there's only one bin, in which case this predicts, yes, there is one way to do it, put everything into one bin. There it is. There's a single bin, put all of your balls into it. All right, so for k equals 1, we've proven the result. Now we assume, doing an inductive proof, that for all n and for all k up to a certain index, the result has been proved. Now what we want to do is show that the desired formula holds for k plus 1 bins. Okay, now the result was that we should have balls minus 1 over balls minus bins. And here we have balls minus 1 choose balls minus bins, which is now k plus 1. So for this particular claim, we're going to now do an induction on n. If n is less than or equal to k, we have fewer balls than we have bins, so there's no way to do this. Recall that the restriction is that no bin can be left empty. So if we don't have enough balls to do it, well, there's nothing to do. We have k plus 1 bins, so if n is less than that, then n is less than or equal to k. Now by convention, okay, I choose j was 0 when j was negative. Okay, if j is less than this number here, the binomial coefficient spits out as 0. So if n is less than or equal to k, then n minus the quantity k plus 1 is negative, in which case this binomial coefficient is indeed 0. So for every n up to capital K, This binomial coefficient correctly predicts there are 0 ways to distribute the balls into bins under the restriction that no bin can be left empty. What if n happens to be exactly equal to k plus 1? Well, now I have exactly as many bins as there are balls. And since no bin is allowed to be left empty, there is one solution. Place one ball into each bin. Remember, the balls don't have labels, so I don't care which ball goes into which bin. At the end of the day, each bin is going to have a single ball. But if n is equal to k plus 1, then this desired formula will eventually resolve down to k choose 0. And if you compute this through its expansion, k factorial over k factorial times 0 factorial, that's going to be 1. So indeed, if n is equal to capital K plus 1, our formula predicts the correct quantity. So now we have assumed the desired result holds for all k up to capital K and all n. Now we're trying to show the result holds for capital K plus 1 bins by inducting on n, and we've accounted for a whole bunch of base cases, everything up to and including capital K plus 1. So now assume the result holds for capital K plus 1 bins and any number of balls up to a certain point. We must show the result holds for that same quantity of bins, but now one larger amount of balls. With the number of bins fixed at K plus 1, we're doing a strong inductive proof on the number of balls. We accounted for a bunch of base cases. Now we assume it holds for everything up to capital N, and we try to show that it holds for capital N plus 1 balls. So now assume we have n regular balls and one special ball. So out of the n plus 1 balls, one of them is special and the rest are not. Distribute the balls into bins. There's two possibilities as to how this worked out. The special ball is by itself or it is not. So possibly some unknown bin got the special ball and nothing else, or possibly the bin that contains the special ball also had other stuff in it, but I don't really care which bin it's in at this point. I'm simply stating there are two possible distributions at the end of the day. The special ball is by itself, or it is not. Okay, so let's just take stock of what we're trying to do. We've assumed the desired formula holds for all numbers of bins up to capital K and any number of balls. We're trying to show it holds for K plus 1 bins by inducting on the number of balls. Our base cases for the number of balls was up to and including K plus 1. So if the number of balls is up to or equal to the number of bins, then we know what to do. Now we're assuming that the desired formula holds for a number of balls up to capital N, and are trying to show the desired formula holds for capital N plus 1 balls. We designated one of these balls as special and the rest as not. There are two ways to distribute them. Either the special ball is alone or the special ball is not alone. If the special ball is in a bin by itself, I still have capital N regular balls, but there's only K remaining bins because I've assumed the special ball is by itself, so remove that bin from consideration for the rest of the balls. So with the special ball taking up a bin all by itself, there are capital N regular balls into capital K bins. That's covered by our inductive hypothesis. For capital K bins, it didn't actually matter how many balls there were. We've inductively assumed the formula works correctly. So if the special ball is in a bin by itself, there are this many ways to distribute the rest. What if the special ball is not in a bin by itself? The remaining n balls can go into any of the bins, including the one that was containing the special ball. And in fact, one of these balls has to go in there, okay, because the special ball was not by itself. That's equivalent to saying that none of the bins can be left empty. Even the one that had the special ball is going to have to get at least one of the remaining ones. So this scenario is also covered by our inductive hypothesis because even in the case of having K plus 1 bins, we've inductively assumed that up to capital N balls is covered by the desired formula. So if the special ball ends up in a bin by itself, the remaining balls go into the remaining bins and none of them can be left empty, and our inductive hypothesis covers that. If the special ball is not in a bin by itself, the remaining balls have to go into all of the remaining bins, including the one with the special ball, but all of these bins have to get at least one normal ball. But since that's K plus 1 bins with only capital N balls, that's also covered by the inductive hypothesis, which spits out this formula. So the total number of ways to do it is either do it one way or the other, so add the two together. Here is the number of ways to do it where the special ball was by itself. Here's the number of ways where the special ball was not by itself. But by Pascal's identity, these two numbers are the same. This was n minus k. This turns out to be n minus k minus 1. So this number is 1 larger than this one. By Pascal's identity, that's going to be capital N, choose capital N minus capital K. And by doing various plus or minus 1s, that's equal to this right here, which is exactly what the formula would predict for capital N plus 1 balls and capital K plus 1 bins. Balls minus 1 over balls minus bins. That's the desired formula up here. So we're actually done. So overall, how did we achieve this proof? The claim was, for all k for all n, the result holds. For k equals 1, we simply showed it's true for any n. So there's our base case. For k equals 1, the remaining bit of the theorem holds for all n. Now we assume our inductive hypothesis. For k up to a certain point, the claim holds for all n. Now what we need to show is that the claim is true for k plus 1 bins and all n, and this claim we do a separate inductive proof on. By inducting on n, we showed the result was true for k plus 1 bins and up to and including k plus 1 balls. Now we assume it's true for exactly this many bins and capital N balls where n is at least as large as k plus 1. Then we have to show that it's true for the same quantity of bins and one more ball, and we were able to do that. So the inductive proof is now finished, okay? We successfully did a separate inductive proof of k plus 1 bins and any number of balls. So having assumed k bins and any number of balls, we showed k plus 1 bins and any number of balls, which concludes a proof for all number of bins and all number of balls. So that's a double inductive proof. There were two variables. We inducted first on k, which then required a separate inductive proof for n for some specific choice of k. By the time we got here, we were saying there are k plus 1 bins, and that is not changing, and then we had to induct on the number of balls. Okay, there was actually another claim in this theorem, the first version, where there were no restrictions on how many balls could go into which bins. That's also a double inductive proof. We're going to omit it in the interest of time. This is already a long enough video, but the desired formula is true. Continuing our discussion of the binomial theorem, suppose a and b are real numbers, not necessarily integers now, and n is a natural number. Then a plus b to the n is given by this sum. The summation, as the index I goes from 0 to n, of n choose I times a to the I, b to the n minus I. This is called the binomial theorem. There's a possible way to do an induction on n. Okay? The inductive step will require some creative rewriting of these sums and using Pascal's identity. Instead, we're going to present a much shorter proof that's just based on counting. It's actually slightly less rigorous. There's a bit of what we call hand-waving in this proof, but by cleverly counting how many ways it's possible to do something, we're actually going to end up with a much shorter proof. So suppose you have a plus b to the n. So you have a plus b times a plus b, etc., all the way to n times. Well, how do you so-called FOIL this out? How do you distribute it? You make a choice of a single item from each term and multiply them together. So choose either a or b and then multiply it by either a or b and then multiply it, etc. So from each term, pick either a or b. There were n possible terms here because I multiplied this by itself n times. So if I choose a, I times, then I must have chosen b the remaining times. There were n possible things to choose, so if I of them were a, then n minus I of them are b. Well, I chose a, I times, and I chose b, n minus I times, and I'm multiplying them all together. Multiplying a by itself, I times, is a to the I, and multiplying b by itself, n minus I times, is b to the n minus I. So any way I can choose exactly I a's will generate this term, because I will necessarily choose n minus I b's. So how many ways can I choose I a's? Well, I can do so once for every way that out of all of the parenthetical terms, I of them I chose A, and the rest of the time I chose B. There's exactly n choose I ways to do that. There were n parenthetical terms, and choose I of them to have a. So there are n choose I ways to generate the term a to the I, b to the n minus I. Since there are this many ways to get that term, I'm going to have that many multiples of that term total. Now I simply sum over all legitimate choices of I. I represented how many times I could choose a. Out of all of these, maybe I never choose a, I choose a 0 times, but at most I choose a n times, and I add up the result. So I here stands for, from the n parenthetical terms, how many ways did you choose a? How many times, I'm sorry, did you choose a? Possibly 0 or anything up to and including n. For the number of times you chose a, you're going to end up with this many ways of choosing it, and you're going to get a to the I, and the rest of the terms give you a b, so b to the n minus I. Related to the study of binomial coefficients are something called multinomial coefficients. Suppose you have k different colors. Okay, so I have n balls, and they are of various colors. Maybe I have 5 colors, okay? Red, green, blue, white, and black, various balls. I decide to make some of the balls the first color, some of them the second, and so forth, up until however many of the balls are the last color. Since every ball has to have a color, the number of balls of the first color plus the number of balls of the second, and so on, if I add them all up, that has to account for all of the balls. Also, the number of balls of a given color can't be negative. So how many ways are there to arrange these balls in a row, assuming that balls of the same color cannot be distinguished, but balls of different colors can? So if I have red, green, blue, white, and black balls, red, red, green is the same as red, red, green, but it's different than red, green, red. So 2 balls of different colors can be told apart, but if I swap 2 red balls, I can't actually tell that I did anything. So balls of the same color cannot be distinguished, but balls of different color can. Well, the theorem is that the number of ways to count such things is given by this formula here. So first, assume that all the balls are distinguished. So not only are there, for example, red, green, blue, white, and black balls, but all the balls have their own individual numbers, so the colors are kind of superfluous. How many ways can I arrange them? N factorial. If I can tell the difference between all the objects, we already know there's n factorial arrangements of n totally distinguishable objects. But now think about each color. I've overcounted arrangements because I can freely rearrange all the red balls. And I can freely rearrange all the green ones, and so forth. So we have to divide out by factors of how many arrangements of the red balls are there, how many arrangements of the green balls, and so forth. So for example, if there are 4 orange balls, the rest aren't necessarily white, they're just not orange. These 2 arrangements are actually the same because the orange balls are in the same place, even though their individual markings have been permuted around. So any way that I can permute around these 4 orange objects is actually the same arrangement. Well, how many ways can I move around these labels? There are 4 of them, so how many ways can I permute those 4 labels? 4 factorial. So for each color, there were ni balls. Therefore, for each color, I've overcounted by a factor of ni factorial. So out of n factorial total arrangements, divide out by all the permutations of the first color and the permutations of the second, etc. And overall, from all the permutations, we've now divided out by the permutations of each individual color, and that's exactly what this term here does. Continuing to talk about multinomial coefficients, okay? The multinomial coefficients can be denoted like this. So as long as all of the ni's are bigger than or equal to 0 and their sum is equal to n, then this right here, which looks a lot like a binomial coefficient but is subtly different, is equal to this expression, this division of all of these factorials. So let's observe, if k is 2, then I have 2 colors, and altogether I have to account for all of my balls, but also n sub 2 must be the difference between n minus n sub 1. That's just saying color 1 plus color 2 is all the balls, and subtract n1 to the other side, you get right here. So for k equals 2, the multinomial coefficient actually spits out the binomial coefficient. According to this notation, you would get this number factorial on top, n factorial, and then all of these factorials on the bottom. But n2 is the same thing as n minus n1. So you'd get n1 factorial, n minus n1 factorial. But this is exactly the binomial coefficient n by n minus 1. So multinomial coefficients represent how many ways to rearrange objects when some objects are indistinguishable from some of them, but not necessarily everything else. Okay. In the case of two colors, arranging objects where there's, for example, white balls and black balls, what you're really doing is choosing which locations get, for example, white balls, and the rest automatically get black ones. So if I choose n1 white balls out of n total, that's the same as choosing n1 white ones and the rest are the other color. So two colors is just the binomial coefficient, and it's honestly the one that comes up the most often, which is why it gets its own special notation. Okay, so when there's only two categories of objects, we'll typically just use the binomial coefficient. Two categories, just pick where one category goes and the rest automatically fills in the remainder. So for example, let's use multinomial coefficients. To permute the digits, I have 3 zeros, 2 ones, and 4 twos. So I have 3 objects that are indistinguishable, 2 objects that are indistinguishable, and 4 objects that are indistinguishable, with a total of 9 objects. So there's 9 total objects, and they come in various categories. One category has 3 objects, one category has 2, and one category has 4. So using a multinomial coefficient, the number of arrangements is given by this multinomial coefficient. The 9 factorial says, just take the 9 objects and permute them, but then divide out by all the ways that the zeros can be intermixed with each other. Also divide out by the number of ways to swip around the 2 ones, and then divide out by the number of ways to permute the 4 twos. Here's 9 factorial, 3 factorial, 2 factorial, 4 factorial. At the end of the day, this counts out 1,260. So how many different ways are there to arrange these digits? 1,260. And no, I'm not going to list them all out. Well, just as we have a binomial theorem for binomial coefficients, there's a multinomial theorem that's going to involve multinomial coefficients. It's a bit complicated to write out. Suppose I have k distinct real numbers, I'm just going to call them x1 through xk, and I have any natural number. All right, if I raise the sum x1 plus x2 all the way to plus xk to the n power, this can be computed as a sum. I have a whole bunch of different indices here. I1 is something between 0 and n. Once I1 has been chosen, I2 is something between 0 and n minus I1. Once I1 and I2 have been chosen, I3 would be something between 0 and n minus I1 minus I2, etc., until finally, once I1 through Ik minus 2 have all been chosen, I sub k minus 1 goes between 0 and n minus the sum of all the indices that have been chosen. That's really what we're doing here. We're saying, first, let an index go from 0 to n. The next index goes from 0 to n minus all the indices that have been chosen before. The next index, I3, would go from 0 to n minus all the indices that have been chosen before, I1 plus I2. At the end, you have I sub k minus 1 goes from 0 to n minus the sum of all the indices that have come before. For each choice of I1 through Ik minus 1, you get this term, this multinomial coefficient, these various powers of all of the x's. Okay, the argument is basically similar to the proof of the binomial theorem. We just need to count how many ways can a single xi be chosen from multiplying together all of these things. In theory, what we now have is an amazing formula that allows us to expand these out quite quickly. In practice, it's very, very specialized. This formula and these multinomial coefficients are pretty unpleasant to work with. So outside of very specialized situations, you really hardly ever see this formula used. The binomial theorem is used a lot. This multinomial theorem actually very rarely comes up outside of specialized combinatorics. Okay, so while the binomial theorem is quite important, this multinomial theorem, it's nice to know it exists. It's nice to know where to look it up. I would not say anyone needs to bother memorizing it.